Let's solve some more problems. So first four problems we saw in our previous session. Now let's look at the fifth one. We have the series square root of n square plus 1 minus square root of n square minus 1. U sub n, the nth term will be square root of n square plus 1 minus square root of n square minus 1. Now, if we take the limit as n goes to infinity, what will this be? You should be able to figure out by looking at this itself. For large n, this plus 1 and minus 1 really doesn't matter. So we are left with square root of n square minus square root of n square, which is basically 0. So as n keeps going towards infinity, the difference between these two goes to 0. So for large n, square root of n square plus 1 is approximately equal to square root of n square minus 1, and in turn approximately equal to n. So as n goes to infinity, the difference keeps reducing and tends to 0. So limit as n goes to infinity of u sub n is equal to 0. That means the necessary condition is satisfied. Okay. Now let's look at the partial sums. Using partial sums, we are going to figure out the convergence. So this is the nth term. Now suddenly, how did this change to this? What we have done is we have multiplied and divided u sub n with its conjugate. So we have multiplied and divided by square root of n square minus plus 1 plus square root of n square minus 1. What happens then? Then we have a minus b times a plus b. So square of this minus square of this. Squaring will take off the square roots. We will have n square plus 1 minus n square plus 1. So n square cancel out, and we have 1 plus 1, 2. And in the denominator, the conjugate will be there. So we have got this now as the nth term. The partial sum s sub n is equal to the summation k equal to 1 to n of 2 by square root of k square plus 1 plus square root of k square minus 1. For large n, same argument. For large n, square root of k square plus 1 is approximately equal to k, and square root of k square minus 1 is approximately equal to k. So, which means s sub n is approximately equal to the partial sum 2 by 2k, k plus k, if we do the substitution. So 2k, 2 cancels out, and we are left with the harmonic series. And we know that the harmonic series diverges, and hence the given series also diverges. Sixth one, we have the series cube root of n plus 1 minus cube root of n. Very similar to the previous one. So the nth term u sub n is equal to cube root of n plus 1 minus cube root of n. Limit as n goes to infinity of u sub n is equal to 0. Same argument. As n becomes larger and larger, the cube root of n plus 1 gets closer and closer to cube root of n. That means the difference tends to 0. And hence the necessary condition is satisfied. Now again, let's look at the partial sum. S sub n is equal to the series cube root of k plus 1 minus cube root of k, where k goes from 1 to n. Now here we actually expand it. Because there is a minus sign here, it would be a telescopic sum. So if we expand it, what do we get? When k is 1, we get 1 plus 1 cube root of 2 minus cube root of 1 plus cube root of 3 minus cube root of 2, and so on. And here terms start getting cancelled out. So cube root of 2, cube root of 2, cube root of 3, cube root of 3. and so on till the cube root of n also gets cancelled out. What we are left with is minus 1, because cube root of 1 is 1. So minus 1 plus cube root of n plus 1. This we take the limit. Limit as n goes to infinity of s sub n is equal to the limit as n goes to infinity of cube root of n plus 1 minus 1. And this goes to infinity. So that means the partial sums grow without bound and hence the series diverges. Now, we have already concluded that this series diverges. But just for practice, let's do a comparison test with a P series. So u sub n is equal to n plus 1 to the power of 1 by 3 minus n to the power of 1 by 3. N we take it out, we get n to the power of 1 by 3 times 1 plus 1 by n to the power of 1 by 3 minus 1. Applying the binomial theorem, we get n to the power of 1 by 3 times, we are applying the binomial theorem to this 1 plus 1 by n to the power of 1 by 3. We get 1 plus 1 by 3 by 1 factorial times n plus 1 by 3 times 1 by 3 minus 1 by 2 factorial times n square and so on, and finally minus 1. So now we start simplifying this. We get n to the power of 1 by 3, 1 minus 1 cancel out. We have 1 by 3 by n plus 1 by 3 times 1 by 3 minus 1 divided by 2 times n square and so on. Again simplifying, we get n to the power of 1 by 3 times 1 by 3n minus 2 by 9 times 2 times n square and so on. Here 1 by 3 minus 1 by 2 is minus 2 by 3. Yes, minus 2 by 3 times 1 by 3 is minus 2 by 9. So that is how we get this 2 by 9. Okay, now simplifying it, 2 cancels out. We have 1 by 3n minus 1 by 9n square and so on. Now, all the denominators contain n common. So let's take it out. We get n to the power of 1 by 3 by n times 1 by 3 minus 1 by 9n plus and so on. Let's take n to the power of 1 by 3 down. We get 1 by n to the power of 1 minus 1 by 3. That is 2 by 3 times 1 by 3 minus 1 by 9 n plus dot dot. Let's take the auxiliary series or the P series as V sub n is equal to 1 by n to the power of 2 by 3, which we know is divergent since P is less than 1. And now we take the ratio U sub n by V sub n, which is equal to 1 by n to the power of 2 by 3 times 1 by 3 minus 1 by 9n plus dot 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 divided by 1 by n to the power of 2 by 3. Converting the division into multiplication and taking the reciprocal, n to the power of 2 by 3 and n to the power of 2 by 3 gets cancelled out. And we are left with this. And now finally we take the limit. As n goes to infinity, what happens? 1 by 3 is a constant, it remains as it is. And in all the rest of the terms, n is in the denominator. That means all the terms disappear. So we are left with limit as n goes to infinity of u sub n by v sub n is equal to 1 by 3, which is a finite value, non-zero value. So since v sub n, series v sub n is divergent, that means the series u sub n is also divergent. Now the seventh one, the series is 2 by 1 to the power of p plus 3 by 2 to the power of p plus 4 by 3 to the power of p plus 5 by 4 to the power of p and so on. If you recollect, this is the Dirichlet series. Anyhow, the nth term u sub n is equal to n plus 1 divided by n to the power of p. Now, here, if p is less than or equal to 1, limit as n goes to infinity of u sub n is not equal to 0, because the denominator keeps reducing and the numerator keeps increasing. So that means the limit u sub n is not equal to 0. That means the necessary condition is not satisfied and hence the series diverges. Straightforward. That is in the case of p less than or equal to 1. Now for p greater than 1, what happens? Limit as n goes to infinity of u sub n is equal to 0. Because in that case, what happens? When p is greater than 1, the denominator keeps increasing much faster than the numerator. Okay. Hence, the necessary condition is satisfied. Let's take the nth term, n plus 1 by n to the power of p. Let's convert it into partial fractions. We get n by n to the power of p plus 1 by n to the power of p. Now, n we take it down, we get 1 by n to the power of p minus 1 plus 1 by n to the power of p, which behaves approximately like 1 by n to the power of p minus 1, because that is the larger of these two as n goes to infinity. Now, let's take the p series as v sub n is equal to n to the power of p minus 1. And take the ratio. U sub n by v sub n is equal to n plus 1 by n to the power of p divided by 1 by n to the power of p minus 1, which is equal to n plus 1 divided by n to the power of p times n to the power of p minus 1. Simplifying it, we get n plus 1 divided by n to the power of p minus 1, which is n plus 1 by n, which we again can split into 1 plus 1 by n. Now we have got it in the perfecto form. We take the limit. Limit as n goes to infinity of u sub n by v sub n is equal to limit as n goes to infinity of 1 plus 1 by n. We know 1 by n goes to 0 and 1 is a constant. So the limit is 1, which is a non-zero finite value. We know that both u sub n, v sub n are either convergent or divergent since u sub n is greater than 0 for all n, v sub n is greater than 0 for all n, and the limit as n goes to infinity of u sub n by v sub n is a finite value. So, in case of the p series v sub n, if because the p series that we had taken was p n to the power of p minus 1. So if p minus 1 is greater than 1, remember in case of p series, we say 1 by n to the power of p. So there, if it is greater than 1, it is convergent. If it is less than 1, it is less than or equal to 1, it is divergent. So that we are applying it here, because we have taken the p series as 1 by n to the power of p minus 1. So if p minus 1 is greater than 1, which implies p is greater than 2, the series is convergent. If p minus 1 is less than or equal to 1, implies p is less than or equal to 2, and the series is divergent. Similarly, the series u sub n is convergent if p is greater than 2, and the series u sub n is divergent if p is less than or equal to 2. So here, very importantly, look at this. The necessary condition is not satisfied and hence the series diverges. That whole process stopped there itself in case of p less than or equal to 1. Now, we said p greater than 1, limit un equal to 0, and we proceeded further because the necessary condition was satisfied. But now what is happening? We are getting a divergent case again. So let's arrive at the upper intervals and understand this. So if P is less than or equal to 1, the necessary condition fails. The series diverges immediately. Now, when P is between 1 and 2, sufficiency fails. The series diverges slowly. And when P is greater than 2, sufficient condition is satisfied and the series converges. So that's how you have to interpret this conditional behavior. Now let's look at the convergence of the series sine 1 by n. So the nth term is u sub n is equal to sine 1 by n. Now limit as n goes to infinity of sine 1 by n is sine 0, which is equal to 0. Because 1 by n goes to 0, we have sine 0 and sine 0 is 0. Hence, the necessary condition is satisfied. Now here the general term involves a transcendental function sine, which means closed form partial sums are not expected. And telescoping is essentially impossible. Hence, we take up comparison test. Sine x is approximately equal to x as x goes to 0, which gives us sine 1 by n is approximately equal to 1 by n. So let v sub n be equal to the series 1 by n, where p is equal to 1, which means the series is divergent. That is, with series v sub n. Now let's take the ratio. U sub n by v sub n is equal to sine 1 by n divided by 1 by n. So now we take the limit. Limit as n goes to infinity of u sub n by v sub n is equal to limit as n goes to infinity of sin 1 by n divided by 1 by n. Now, when n goes to infinity, 1 by n goes to 0. And we know limit as x goes to 0, sine x over x is equal to 1. So, which means that the limit as n goes to infinity of u sub n by v sub n can be written as limit 1 by n going to 0 of sine 1 by n by 1 by n, which is equal to 1. Here basically we are changing the variable n to 1 by n. So as n goes to infinity, that we can replace, we are replacing it with 1 by n goes to 0. So which means u sub n is sine 1 by n and v sub n is 1 by n, which is equal to 1, which is a finite non-zero value. So since v sub n is divergent, so u sub n is also divergent. That was convergence of infinite series, the second set of problems. Now, if you found this session helpful, please do like, share, and subscribe. Comment suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.